Namaskar, welcome back. So, this was the last part where we stopped in the previous lecture, and we were discussing about the phases model, and this is mainly related to the scarp degradation part. Okay. So, how we differentiate between the debris phases and wash phases. Wash phases will be a little bit away from the faulted surface, and debris phases will be closer to the faulted surface. And also, these are the criterias or the indicators which one can use to differentiate between the debris and wash phases. Debris will be much coarser, whereas the wash phases will be finer deposits. Okay. So, based on the erosional material, what we call the colluvial material, the word colluvial wedge was evolved, and that several scientific group took into consideration to identify the number of events. So, based on the number of colluvial wedges you see in the trench, you can correlate that with the different events, okay, because they have formed after the event. So, this figure which is on the right hand side of your screen shows that how this is a schematic figure, but it shows that how colluvial wedge or the colluvial material can be considered towards identifying the ancient earthquakes or paleo earthquakes. So, let us move and see what exactly this has to tell. Now, in figure A, if you see, then this part is your we can say the surface which existed before. So, this was the surface here. Okay. So, this is the surface, the same surface. Now, this was down faulted because we are talking about the normal fault. So, this was down faulted along this fault plane as the movement was. This is the hanging wall and this is your foot wall. So, the right hand side wall has moved down and the displacement which was observed was almost like 2 meters. Okay. So, this is event 1. Then after the erosion of the scarp, now we are looking at the B. Okay. After the erosion of the scarp and deposition of the colluvial wedge. So, this material which was been eroded from this portion, okay, has been deposited here. The slope has been stabilized, okay, and finally you have the you may see a sort of an wash faces here. Okay. So, this is your colluvial material. Similarly, if you get into the third stage, which shows that there is a deposition. So, when this phase initiated, okay, this one, it resulted into the deposition of 1.5 meter of alluvium here. So, this is the filling up which has gone up to this level, you can say, and there was a deposition over here. Okay. So, as what I was talking about, that you may come across the wash faces, but at the same time you see that there was a deposition over here. So, this alluvium was deposited after the event 1, and also we have the preservation of this colluvial material over here. So, this is a process which has happened over the time where the scarp was, because this we will call this as an fault scarp. Okay. So, this fault scarp was subjected to erosion, and then finally what we see is the process of erosion followed by a deposition, and that deposition resulted into the accumulation of sediment as thick as 1.5 meters. Okay. So, this is your deposition of that alluvium. At another point which one can note, that if you, for example, after a decade or so, you go in field and you try to see that there is a scarp here. Okay. So, what you will identify is the scarp only. Okay. So, if you go in the field and try to see this, then it will be something like left out exposed one will be 1.5 meters only. Okay. Because the 2 meter, because this 1.5 meter is 0.5 meter is visible, but 1.5 meter is been covered up by the deposition. So, depositional phase has covered that. So, sometime this also is this part is important, because what happens is that we see a very less displacement in the field, and displacement has a direct relation with your magnitude also. Okay. So, if the amount of displacement, if you have seen, is less, then you may say that it may be an erosional feature, or it may not be related to the tectonics. And if at all it is a tectonic feature, then the earthquake would have occurred, which would have been with a very low magnitude. Okay. So, this is another misinterpretation we can gather. Okay. It is not our mistake, but it is the topography which tells us. But back of the mind, one should keep that and see whether there is an deposition which has occurred in the past or not. Okay. After the event, okay, after the earthquake, whether the deposition has occurred or not. And this you can see only if you expose the section across the fault. Okay. So, this is another point. Okay. Now, when you have the second event, event 2, then you will see that the event it will definitely takes place on the same fault. So, now the second event has resulted into the displacement of almost like 2 meters here. So, what we saw was this was only left out 0.5 meter, which comes from here, okay. But again it has raised the scarp. Okay. So, what you will be able to see that this 0.5 meter is from the previous residual section which was available, and then 2 meter has been added. Okay. So, total height will be your 4 meters, but you will have to see the topographic breaks which have been seen in this. Okay. So, topographic break, when I say, is this one. Okay. So, one is this here, and another is, you say, this one. Okay. So, there is a break here, topographic break. Now, this topographic break has different slope as compared to the slope which has been seen here. So, if we say this is, for example, your slope 1, okay, and this is your slope 2, there is a difference in angle. That also can be taken into consideration to say that there were 2 events. Okay. And this topographic break and change in the slope what you see in the on the fault scarp is related to the 2 events and not the single event. Okay. So, now coming to this 4 meter, we get from this displacement, that is the displacement we had in the second event, okay, and the displacement which we had of 2 meters from the event 1. Then third one, again you will have an erosion and then deposition, and that will result into the left out scarp height of 2.5 meter. Now, in this case, the slope is a single slope you see, because the erosion will start from the S1 slope. Okay. Because S2 slope is the fault scarp, that will degrade, and then this will start. So, the deposition will somewhere take place over here. So, the colluvial which has been shown here is been deposited over here. Okay. So, this is the basic idea about. So, when you open up the section, then you will be able to see the colluvial wedge. Okay. So, this is colluvial wedge 1 and this one is colluvial wedge 2. So, that part you will be able to understand only and only after you open up the trench. Okay. Otherwise, you will say that this is an one single event scarp, okay, which is not correct. Of course, first instance you may be okay with this because you see a single slope, there is no break in the slope, but at the same time you see another important point which one has to keep in mind. Okay. So, this could be one of the interpretations you can have, that is your single event scarp. But when you try to look at figure B, okay, that is after the first event, of course, there is a deposition and all that, or you just go to figure A, okay, then what important part which one has to see is that whether the surface which was together, for example, if I see put the pre-faulting surface, then it will be something like this with this slope. Okay. So, that faulted surface is having the same slope, but at the end in figure E, if you see, and even in figure B, you will find that the slope is not the same. Okay. The slope of the faulted surface is different. This is almost flat and this has some sort of an angle here. And same goes with the even after event 2. Okay. The slope here is not the same. Okay. The slope is different actually. So, you have inclination in this slope, inclined, but this is flat. Okay. So, uh, these are all signatures which one has to look at. Okay. So, same description has been given here. Okay. That first event, if we see the displacement of uh, sloping surface which is around 5 degrees, okay, which is gentle sloping surface, erosion of the scarp and deposition of colluvium, aggradation of 1.5 meter post faulting alluvium buries the lower 3/4 of the fault scarp, that is your B. Then second event occurs, that is your figure C. Okay. Again the displacement was 2 meters, erosion of the scarp and deposition of second colluvium wedge. So, colluvial wedge has been deposited over here. So, this is a deposition of the second D. Okay. Then finally, sorry, this one is, so deposition will take place over here, and then finally E, what we see is the total scarp height 2.5 meter. It is not equal to either single event or double event displacement. So, if we see the 4 meter of displacement, net displacement over here, the scarp which has been seen, okay, is not to the, but that again as I told, that can be only achieved, or you can get this information of the 4 meter if you have opened up the trench. Otherwise, you won't be able to see this sloping surface. This you won't be able to see. So, when you match this, then this is 4 meter, because based on this only it has been marked, okay, the sloping surface and the surface which is exposed. This is buried, but this one is exposed. So, sloping surface on the hanging wall and the foot wall, when it is measured, it shows 4 meters, okay, displacement, net displacement. But when you see the exposed scarp, then it is 2.5 meter only. So, this variation in the height and the amount of displacement does not matches. So, those are few points which one should keep in mind when you open up the trench, and same goes also for the reverse faulting. Okay. Now, compound faulting scarp, as we have discussed in the previous sketch, okay, and the schematic diagram, this is again another one, that C and C dash are the scarp, because this is quite steeper and this is quite gentler. Okay. So, these are the two scarps which have been formed in multiple events. Okay. Of course, the C part, okay, C to C dash if you take, then that sloping surface has been eroded and stabilized. But new scarp which has been developed is from C dash, or you can say B here, okay, and C dash B, that line is your new scarp during the event. So, this is an example again of unfaulting from Mexico. Now, this has slightly oblique displacement. So, do you have normal component, normal faulting, plus you have an oblique, and probably if I am not wrong it is left lateral movement. So, this is a scarp here which is clearly seen, visible after the event, okay. And they have also done LIDAR, okay, mapping, and LIDAR mapping clearly shows what we were talking. Okay. So, the stream is coming from here, you have this is the stream which is flowing over here, and then the connecting stream is over here, you can see. Okay. So, this block has moved like this as well as it has moved down. Okay. So, this block has moved aside. So, this is not left lateral, but yes, this is not left lateral, this is right lateral. Okay. This is a right lateral movement because the stream is been shifted towards us. Okay. This is typical of, so down faulting. So, you have, so previously as I was talking about that it was not clear whether it was right or left, but from this it is very clear that this is right lateral, and plus you have the normal faulting. Okay. So, you have right lateral movement plus you have normal faulting, and same you can see here also. If I put the stream here, it goes here and then you have this stream. Okay. This is a typical right lateral with normal component. Now, relation between the geomorphic surfaces and fault scarps. Now, in field, if you go, or the natural processes where the landscape evolve, we have learned about the fluvial landscape, we will see the terrace formations and all that. Okay. Now, this terrace formation is a natural process which is taking place, as well as the because of the erosion and deposition, but at the same time if you have the events which are occurring periodically, that will also get preserved in these landforms. Okay. So, how we see this type of landforms where you have the terrace formation. So, one, if we talk about, then for example, you have a stream here and then there is a formation of terrace. Okay. So, this formation of terrace again is almost like what we see, and we can say this is an erosional scarp. Okay. This is not tectonic scarp, but suppose this gets displaced, okay, along this fault. Okay. So, if the fault is running over here, then if this has been displaced, for example, it moves like this. Okay. And also it has a component of down faulting, then how it will look actually. Okay. So, I will try to sketch if possible. So, you have the movement of this. Okay. So, this portion you will see is been displaced and exposed. Okay, if this has moved down, okay, and this portion has gone up along the fault. Okay, so for example, this block has moved up and this block has gone down. Okay, along this fault, then you will be able to see a sort of an escarpment over here, because this will be in fault scarp actually. Okay. And then you have, so this fault scarp is also termed as this as an terrace risers. This we will see that how we can have the correlation between and what are the relation between the geomorphic surfaces and fault scarps. Okay. So, this is an example of again from New Zealand. Okay. And what we see here is that uh, the faulting environment is right lateral strike slip. Okay. And that has resulted into, of course, you have terraces, but at the same time you also see the fault scarps. Okay. So, these are the hill slopes which are, we can say, the erosional scarps. Okay. These are erosional scarps here. Okay. But at the same time what you see is also the fault scarps. Okay. So, if such scarps are exposed, then we say that these are all like indicative of the terrace riser. Further example from this, again an anaglyph, you need to have the filter glasses to see this image in 3 dimension. Okay. So, here also we see that there was a fault which is running over here. Okay. So, and that fault was responsible for displacement of the stream in this direction, but at the same time it also uplifted this portion. Okay. And this portion is, but here we have the component of reverse faulting, not the normal faulting. Okay. So, this side is up, this is down, and it has developed a scarp here, okay, as well as the offset of the streams. So, what we saw that as you move from this portion towards the stream, major stream, this is a major stream, if you move towards that, then you see a sort of steps which have been seen here. So, there is one step here, then another step here, third step here, and fourth step, and then you have a cliff, a deep cliff here. So, these are indicators of your terrace risers. Okay. But the fault scarp is sitting here. Okay. This will be the fault scarp. So, this is a fault scarp here, and these are all what we call the terrace risers. Another example that we tried to rematch this. Okay, that how many events could have occurred. Okay. So, this is the way we keep doing and try to understand that what will be the amount of displacement along this fault. Okay. Another example of terrace riser. So, we have this block diagram which is depicting the geometric elements of faulted terrace risers. Okay. So, here what we have is that we have a fault here which crosses this line. Okay. And the movement is your left lateral. Stream which is flowing over here. So, this is the active stream. Okay. You have an active stream. So, what active stream will do is that it will result into this erosional surface. Okay. It will result into this erosional surface. Okay. And this one here. Now, this has been displaced along the fault. Okay. The displacement is over here. Okay. So, you can clearly see that there is a fault scarp here. This will be the fault scarp. Okay. We can say this is a fault scarp, whereas this one which I have marked with the yellow part. Okay. Let me put this here. These are your terrace risers. Okay. I will stop here and we will continue with this discussion in next lecture. Thank you so much. Namaskar.